Hello everyone. In this presentation, we are going to demonstrate the Smart Fuel Safeguard System. Fuel theft is a significant challenge faced by industries relying on fuel-powered vehicles and machinery. Unauthorized fuel extraction not only causes financial losses but also disrupts operations and compromises security. These are few fuel theft case studies that highlights the significance of a project. To address these issues, our project, Smart Fuel Safeguard System, develops a real-time monitoring system that detects and alerts users to unauthorized fuel extraction. Here are few diesel theft incidents.
சரி ஒரு 5 மணிக்கு கிளம்பி போகலான்ட்டு ஏஞ்சி பார்க்குறேன். இந்த மாதிரி டேங்கை உடைச்சிட்டு டீசலில் தான் எடுத்துட்டாங்கண்ணா.
The hardware components we used are two Arduino Uno boards, two NRF24L01 Bluetooth modules, an ADXL 345 accelerometer, and a buzzer. This is a tank side unit, and this is the ADXL 345 accelerometer which we have used, and it is used to detect the change in acceleration in all three axes. This is the NRF Bluetooth which we have used. We have specifically used this Bluetooth module so that it facilitates wireless communication with a decent range of about 20 meter to 30 meters, and it is also cost effective, which is an added advantage. So as soon as the ADL XL345 accelerometer detects the tampering action, it sends signal to the Arduino Uno board. This Arduino Uno sends back the signal to the Arduino Uno board which is present at the driver side via this Bluetooth module. This is the driver side unit. As soon as the microcontroller receives the signal, it turns on the buzzer, and as a result the buzzer rings, indicating the tampering action. Additionally, we have installed a switch which is used to turn on or off the system based on the user's requirement, which makes it power efficient. Now we'll move on to the demonstration. Now I'll turn off the switch. This is the block diagram. As we saw, the ADXL 345 sensor is capable of detecting the change in acceleration in all the three axes X, Y and Z. As soon as it detects the vibration, it sends signal to the microcontroller, and the microcontroller in its turn sends the signal to the Arduino Uno, which is present at the driver side unit via this NRF24L01 Bluetooth module. And after receiving the signal, it turns on the buzzer. So the buzzer rings. There are certain registers which are associated with the tap detection. So these are the registers which we have used for our project. So these indicate the register address. So first one is the tap access register. The value we have used is 0x07, which enables all the three axes X, Y and Z. The main purpose is to ensure the tap detection regardless of the sensor's orientation. It enables all the axes, which actually improves the detection in any direction. Disabling specific axes can also help filter out irrelevant movements. Next is the thresh tap register. This defines the acceleration threshold that a tap must exceed to be detected. The value we have used in our code is 50. That is, the impact of a tap should exceed 50 to be even considered as a tap. If the value is below 50, the tap would not even be considered. The purpose of this is that it helps distinguish between light taps and strong taps. When the value of the register is low, it can detect low taps. If the value of the register is made high, then only stronger taps would be detected. Next one is the tap duration register. This sets the maximum time acceleration that the tap must remain above the threshold to even count as a tap. The value we have used in our code is 30. The tap would be considered only if it sustains the amount of time which we have specified in the register. So the main purpose is that it helps differentiate between sudden impacts and sustained forces. The impacts in real time are shorter duration detects sharp taps, whereas it ignores longer touches. Next is the tap latency register. it defines the waiting time after a single tap before a second tap can be registered. The value we have used in our code is 80. That is, after a single tap has been observed, within the specified time, if another tap is observed, it wouldn't be considered as a double tap. It would remain as a single tap detection. So the main purpose is to prevent false double taps by ensuring enough delay between the taps. Longer latency ensures deliberate double taps, but it feels unresponsive. Next one is the tap window register. It defines the time frame in which a second tap must occur after the first one for it to be recognized as a double tap. The value we have used in a code is 255. After a single tap, if the second tap occurs within the value specified in the tap window register, it would be accounted as a double tap. If the second tap comes after the time specified in the register, it would be accounted only as a single tap. The main purpose is that it defines how quickly the user must perform a second tap for it to be valid. Shorter window requires fast double taps, which is not the case in longer window. The final register is the interrupt enable register. This register is used to enable both single and double tap interrupts. If we only need to enable the single tap interrupt, the code we'll be using is 0x20. If we need only double tap, that's 0x40. Since in our project we need both the single and double tap interrupts to be enabled, we have used 0x60. The main purpose is to allow the accelerometer to notify the microcontroller upon detecting the tap event.